Okay, so today we are going to start chapter 16 of R.C. Hibbeler book. It's planar kinematics of a rigid body. So far what we were doing, we were considering particle and we did kinematic analysis of particle and then we went towards kinetic analysis of particle. So now in today's class, we will start studying about rigid body kinematics and then after kinematics, we will go through rigid body kinetics. Okay, as I have told you that this is chapter 16 of your R.C. Hibner book. So, what are the objectives of this chapter? So, the first objective is basically to classify the various type of rigid body planar motion, means to understand what type of planar motion can we have. Then to investigate the rigid body translation and angular motion about fixed axis. Okay. Then to study planar motion using an absolute motion analysis, to provide a relative motion analysis of velocity and acceleration using translating frame of reference, then to show how to find the instantaneous center of zero velocity and determine the velocity of point on a body using this method, and finally to provide relative motion analysis of velocity and acceleration using a rotating frame of reference. So these are basically the few of the things which we want to achieve, or these are few of the objectives which we want to achieve with the help of content that we have in this chapter. Okay, so as I have told you, we are continuing with rigid body planar kinematics. So at first, we will consider rigid body planar motion translation. As I have told you that we can have different types of rigid body motion, and again in rigid body space motion as well as in planar motion, again we can have further or we can have subtypes. So in this class, what we will consider rigid body planar motion. And in that planar motion, the first one that we are going to consider, that is basically translation. Okay. Uh, Definitely the question arises in everyone's mind that why we want to go for a rigid body analysis. Since we have already done our particle analysis, why we can't consider each and everything as a rigid body? So in most of the cases, the size of particle that basically play an important role. For example, if you look over here, we are having few applications, and all those applications, if you want to observe them, so in each of them, the size is playing an important role. And we know that by increasing the size, the force that basically act on the object, uh, it is having different mechanism. Means there might be on particle we might not be having moment, means all forces act on that single particle. But if the size of particle increases, means if the size of object increases, if we do not consider as a particle, this means forces are spread over all that object. So those forces can have direct effect and they can also have moment. Okay, so these are few of the applications which have been shown here in this diagram or in this slide. So since it's having a number of applications, that's why it's very much important to study it, to understand, to analyze these daily life applications. Okay, so before going into the planar motion or the various type of rigid body motion, let's discuss that rigid body motion. So rigid body motion is basically more complicated than particle motion. Why? Because it's involved not only translation but also rotation. For example, this is rigid body. So this rigid body, it can translate, it can move like this, and it can also rotate, means about its fixed axis, right? So it can have that motion, and during that motion, it can also have that rotation. So you can see over here that the orientation of this object is changed. So rigid body motion, due to this reason, is more complicated as compared to the particle motion because it involves translation as well as rotation. Okay, if you want to compare both particle and rigid body, so what we can have, let's see. Okay, particle for particle, the characteristic that we have, it's on the left side, and for rigid body, we are having it on the right side. Okay. So in case of particle, usually we ignore the volume. Particle is considered to be a point, whereas in case of rigid body, volume cannot be ignored. Rigid body can be of any shape. It can be like some disc, it can be some slab, etc. Okay. Particle can undergo only translation motion, but as we have discussed in the previous slide, that rigid body can undergo both translation as well as rotation motion. Then all forces are through means all forces are basically considered or thought of acting on the same point. No need to check moments of particle, or in case of particle, there is no need to check moments. But in case of rigid body, moments are relevant in rigid body. Both resultant force and resultant moment is required to be satisfied for equilibrium, right? Okay. Let me explain this point. Mean, if we are having particle, force are acting, another force is acting, another force is acting, all forces are acting on this single point, right? Because particle is considered as a point. And if we have some rigid body of any shape, one force is acting here, one force is acting here, and one force is acting here. If we want to find out the resultant of all these forces on this point, so we will not be having only the forces, but this force will be having moment about this point due to this perpendicular distance, and this another force, it will also be having moment about this specific point due to this perpendicular distance. So that's why we need to consider both moment, resultant moment, as well as resultant force. Okay. So in this chapter, or in the initial section of our course, what we are basically considering, we are focusing on planar motion instead of three-dimensional motion, which means that during motion, the path of any given particle in this rigid body, that is basically limited to a plane. And okay, let me remove this one. Okay, so in case of planar motion, means the motion of particle, that is basically limited to a plane, means the motion of particle, the motion of rigid body, it can be either in this plane, or it can be in some other plane, or it can be in some other plane, right? But one thing that we need to consider, or that we need to remember, that all these planes, means they are basically parallel, and they are equal distance, means they are having equal distance from a fixed plane, right? So you can see that in this case, the object is having translation as well as rotation. So you can see this object, means this surface, this section, it is traveling in this plane, right? The second section that we have over here, it is basically having motion in this plane, and this one is having its motion in this plane. Okay. So here in this class, what we are doing basically, we are trying to focus on planar motion, not on three-dimensional motion. This means that the motion in this case, it will be basically limited to a plane or within a plane. Okay. So rigid body planar motion, in case of rigid body planar motion, we can have different types of motion. Means the object, it can move in a straight line, it can have translation, it can move a straight line, it can move in some curve. So that will be basically considered as translation. And the object basically can rotate about a fixed point, or another word, it can rotate about a fixed axis, right? This can be like the axis, and this object can rotate about this fixed axis. So that is rotation about fixed axis. And then we can have general plane motion. In general plane motion, the object will translate, and along with translation, it will also have rotation. Means this object will rotate like this, and it will also translate. So that is basically known as general plane motion. Okay. So during translation, the path, for example, if you consider any two particles, let's say this is particle A and this is particle B. Now let's say the object move from here, or the rigid body move from this position till this new position. So the points that we were having initially, they are basically following some path, right? So during translation, the path could be a straight line as shown over here, the path followed by both the particles, which is basically called rectilinear translation. So means if the translation is along a straight line, if the path that the translation follow is a straight line, so that type of translation will be known as rectilinear translation. But if the particle move from one place to another new place, and the path that it follow, if it is along some curve, means let's say this is, and then we have this one, right? So if this object move from this place to a new position, the path that it follows, or the path that the particle follow, if it is a curve path, so in this case, the translation that we'll be having will be known as curvilinear translation. But we need to remember that either way during translation, for any 2 points on this rigid body, their paths are identical. Means, for example, if we go back, so the path that this point follow, that is from here till this point, it is identical as the path followed by this particle. And similar is the case with this one. The path followed by this particle, it is identical with the path followed by this particle. Or sorry, I was using this word particle. Instead of particle, we can use the word point. And the path followed by this point is same as the path followed by the second point. Means both are identical in shape. Okay. So now over here, I have given this. Let me remove this. Okay, these figures are basically from your book. Okay, so over here we are having this particle, not a particle. Sorry, we have a rigid body. This rigid body is moving from one place to another. So in this case, let's consider any 2 points. They move from here till this point, and they are following a straight path. So this is basically rectilinear translation. And now in this case, these two particles are following some identical curve path. So this is basically curvilinear translation. In this case, the object is rotating about a fixed axis. So this is known as rotation about a fixed axis. Okay. And now in this case, we are having these 2 points. These 2 points are basically following some curve path, and this object or this rigid body is also rotating about a fixed axis. So you can see over here, in this case, we are having translation, curvilinear translation, as well as rotation about a fixed axis. So this one is basically known as general plane motion. Okay, here is an example of a different combination of motion that we can have in real life system or in real life machine system. Okay, so you can see now, if you observe this object, this point, it can move like this, and this one basically can move. This one can rotate like this way. Okay, and over here, this section, it can basically move to and fro. It can move backward and forward, and this rod connected with it, it can also have this motion, and it can also have that combined rotation. Okay. So what we have over here in this system, we are having rectilinear translation. Now this component, it is having a general plane motion, that is combination of translation as well as rotation. Okay. This component is basically following path like this. That means when this rotates, so it moves like this. So this is having curvilinear translation, and this portion and this portion, they are basically rotating about a fixed axis, so they can have rotation about fixed axis. Okay, sorry, I have made a mess of this diagram, but I hope that you understand. Okay, now let analyze translation using relative motion. Let us consider that there are two arbitrary points on this rigid body, and let's say these points are point A and point B. Okay, so to analyze them, let's say we make, or we have a coordinate system over here. Let's put our coordinate system on this point, that is x, y, and z as shown over here, right? Let's make another coordinate system on this point, and that coordinate be x dash, y dash, and z dash as shown in this diagram. Now, what is the difference between the coordinate system x, y, z? So the coordinate system, that is x, y, z, this is basically a fixed coordinate system at point A. Means this coordinate system will be considered, or the origin will be considered, this point A in over here, it will be considered as origin. This coordinate system will not move. Now in this case, the coordinate x dash, y dash, z dash, they will not remain at this origin. Means if point A moves, if this object moves, definitely point A will move. So these coordinates x dash, y dash, and z dash will also move with point A. So that's why I have shown over here that xy, let's xy be xyz be a fixed coordinate system with origin at point A, and x dash, y dash, z dash coordinate system at point A, that will translate with point A if point A translate. Okay, so let's say object A, means this rigid body moves from this place to this new position. So as I have told you, x, y, z will be basically the absolute coordinate system, and that x dash, y dash, z dash coordinate system are the origin of x dash, y dash, z dash. It will move with the rigid body. Okay, now to find out the position of point A with respect to the absolute coordinate system, we have this RA. What is RA? That is basically a position vector, right? Or we can say this is a vector that measures the position of point A with respect to fixed origin, and that RB basically measure the position of point B at new position with respect to the fixed origin, right? And what is that RB by A? RB by A is basically the relative position of point B with respect to point A, or with respect to the new origin, right? And we know that relative position of B relative to A can be given by this equation, which we have already understand in our previous lecture. So RB by A can be given as RB minus RA, whereas RB and RA are basically the absolute position vectors. Okay, so during translation, as we know that RB by A means if this object is moving, so the relative position of point B with respect to point A, that remains constant. It remains same. It doesn't change. So if we take its time derivative, what we will get? We will get 0. If you take time derivative of constant, so you will get 0. This means that if we take time derivative of this RB by A, and we know that what we get if we subtract the final position from initial position, so we basically get displacement. So if you take time derivative of displacement, so what we will get? We will get basically the relative velocity of point B with respect to A. So this means the relative velocity of point B with respect to A, that will be 0. And again, if we take time derivative of velocity, so what we will get the relative acceleration of point B with respect to A. Again, it will become 0. So what that basically conclude that VA is equal to VB, or acceleration of particle of point A is equal to acceleration of particle B. This means that during translation, all particles in the rigid body will always move with the same velocity and acceleration at all the time. Okay, so now here we are having this short question, that which is a type of rigid body planar motion. So planar motion, as we have studied, what will be included in that rigid body planar motion? Can it be translation? Can it be rotation about fixed axis? Can it be general plane motion, that is combination of both? Or can it be option D, that is all of the above? So you need to go through the slides, think over it, and then you need to select one of the answer. Okay, so here I have an example that I have taken from your book R.C. Hibbeler. This is example 16.1. So what this example is basically saying, kindly give me a few seconds. I think it will be better if we do this example uh, after going through the second part. Okay, so kindly remind me when we do that second part, then I will come towards example 16.1. Let me change its position so that we don't forget. Okay, so let's start the second portion of our today's lecture. Uh, as we just discussed the translation, so now we are moving towards the rotation about fixed axis. And remember that we are studying rigid body planar kinematics. Okay, so for rigid body planar motion, as we know that rotation is limited within xy plane. For example, if we have this xy plane, so the rotation will be within this xy plane, and it's look like rotation is only about fixed point. For example, we have this point, so usually it looks that rotation is about this point, but in reality what happens, that rotation is not about a fixed point, rather than it's about a fixed axis like this one, but that axis passes through point O, right? And it is perpendicular to the xy plane. For example, if this is that axis. So that axis passes through point O, and this is perpendicular to both x and y. If we have x over here and y over here, so that z is basically perpendicular to it. So that's why we call it as rotation about a fixed axis. Okay, now let us consider a rigid body, planar motion, or let us consider a rigid body rotation in case of planar motion. So let's have 3 points. Let this be the point, then another point, let it call as, let this be P1, this be P2, and this one as P. And this is that fixed point, or let's say uh, this is a point through where the axis passes, about which rotation takes place. Now, as we have discussed that in case of rotation, the object rotate about a fixed point or about fixed axis. So this point P, it will rotate about this point O, right? So it will follow certain path. Then this point P again, it will rotate about this point O again. It will follow some path, and this point P1 again, it will rotate about that point O, or about that axis that passes through point O. So we can have three different paths. So for point P, the path that it follow, this is this circular path. Then for point P1, the path followed is this one, and then for point P2, this is basically the path, right? So let's say if we draw a line that start from origin and that passes through cross section of all these three paths, let be this line. Okay. Now after a certain time, let's this point P or this line move from here. Let's consider this point P. It moved from this location till this new location over here, as shown in this diagram. Okay. So initially we were having this line, we were having point P over here. Now after a certain time, the rigid body rotates. So what happened? This point P moved from here till this new position. Now this angular position of point P can be given by theta. The unit of theta is basically radian, and we know that it's a dimensionless unit. Okay. Similarly, the angular velocity that the particle had, it can be given by omega, and we know that omega can be calculated by the time derivative of angular position or angular displacement. Similarly, the angular acceleration can be determined by taking time derivative of angular velocity, and that is further equal to double time derivative of angular position or angular displacement. Now, if you combine this equation, that is angular velocity and angular acceleration, and from here if you eliminate theta value, so what we can get basically, we can get a new equation, right? So in this case, like three basic kinematic equation that we were having in linear motion, we had two kinematic equation for angular motion, and we derived third one by combining these two basic equation in case of angular motion. So as we had three basic kinematic equation for linear motion, one was for velocity, one was for acceleration, and one was combination of both of them. Now we are having the same sort of three equations for angular motion. One is for angular velocity, one is for angular acceleration, and one is basically obtained by the combination of both these two. Similarly, we had equation of motion. We had basically equation of motion for constant acceleration, if you remember, in case of linear motion. So these were basically the equation, right? So we can write, or we can have the same equation for constant angular acceleration case. These were the equation, the one on the left side for constant linear acceleration. Now we can have the same equation for constant angular acceleration. But over here, instead of displacement, we'll be having angular displacement. Instead of displacement, again, angular displacement. In case of velocity, instead of acceleration, we will be having angular velocity and angular acceleration. So here we are having three basic kinematic equation for angular motion. Okay, as we have already discussed that for rigid body planar motion, rotation is limited within xy plane. As we just discussed, that rotation will be within xy plane. Therefore, Cartesian vector, angular position, angular velocity, and angular acceleration all have component of k. Okay, the rotation is like this. That is within xy plane. So by right hand rule,
Sir,
for example, if you want to find, yes,
sir, इनकी डायरेक्शन परपेंडिकुलर टू द प्लेन होगी.
GG exactly. So as you have said that this direction will be perpendicular to the plane. So if this is xy, if this is xy, so perpendicular to the plane will be z direction, right? And the unit vector along that direction is basically k, right? So that's why we say that angular acceleration or angular position can be given as magnitude and unit vector along z direction. Similarly, angular velocity, it will be having direction in the z, or similarly the angular velocity and angular acceleration both will be having direction along z axis, in which we are having a unit vector k. And as you have just said that why we are having this direction, because the direction will be perpendicular to the plane xy, and to the one that is perpendicular to the xy is basically z axis, and the unit vector along z axis is k. Okay, now sign convention. Uh, you can change this sign convention for yourself, but usually for this book or for our problems, what we will follow, that acceleration, angular acceleration, it will be considered angular acceleration, angular velocity, as well as angular displacement. It will be considered as positive if it is in anti-clockwise direction, and it will be considered as negative in clockwise direction. Okay, so these are the direction basically for positive motion, positive angular motion. Okay, now one more thing that we need to understand, that usually particle is idealized as an object with no size and no shape. Means we say that particle is an object that is having negligible dimension, right? So this means that an object having no dimension, or we, if you can say, if it is like a point, then this means the particle can never rotate. Means if there is zero dimension, so how it can rotate about a fixed point, right? This point it cannot rotate. This means that during rotation, that particle in the rigid body, that basically does not undergo rotation, right? Rather than it follows some curve path, and we know that if a particle follows some curve path, that motion is known as curvilinear motion, right? So as a whole, the rigid body will be having rotation, but the different points that we will be having are the particles, the different particles that we have on the rigid body, they will not have rotation. They will undergo a curvilinear motion. So during rotation, particles not on the axis of rotation in the rigid body undergoes curvilinear motion, right? Means, for example, if we have particles on the axis, okay, if we have particle on the axis, so definitely these particles will neither rotate nor they will follow any motion. Means they will not be having any curvilinear motion even, because they are on the axis, on the fixed axis. But the particle that is over here, it will follow some curve path. The particle over here, it follow some curve path, and the particle over here, it will follow some curve path. So particles in the rigid body do not have basically that rotation. Rather than they are having linear acceleration and linear velocity. For example, if particle is following this curve path, so during that curvilinear motion, the particle can have velocity with two components. One this one, and one component like this. This one is known as tangential, and this component is known as radial component, right? Okay, so now let us consider a particle P. We want to consider the motion of particle P. As I have told you that if we are having particle, so it cannot undergo a rotation, rather than it will be having curvilinear motion. So let us consider that motion of particle and let that particle be P. Okay, so curvilinear motion of point P, as I have told you that it's following some curve path, so it will be having two components. The velocity can have two components, but usually the direction of velocity is given as tangent to the path. So this is basically tangent to the path, and that's why we have shown velocity like this. Okay, and the position vector, or the vector that is basically showing the position of that point P with respect to origin, let it be called R. So R is basically position which is giving the position, or which is showing the position of point P with respect to this origin, right? And definitely this is perpendicular to the direction of velocity. So as we have studied in our previous classes, that in case of anti-coordinate system, in case of velocity of particle during curvilinear motion, the velocity component can be given as, the velocity can be equal to the magnitude of velocity into the tangential component, right? There will be no radial component in case of in case of curvilinear motion. Okay, similarly we know that the magnitude of that velocity, that is basically equal to the rate of change of displacement, right? And what is this, is as this is basically displacement, and we know that that s is equal to, in that linear displacement is equal to angular displacement if it is multiplied by r, right? So instead of this, as if we put over here r theta, so what we will get, we will get this equation, r into d theta by dt. So d theta by dt, that is basically the time derivative of angular displacement, and it will gives us angular velocity. So this is very famous equation which we know, that v is equal to r omega, v is equal to omega r. That basically gives us the relationship between linear velocity and angular velocity. If you want to write it down in terms of vector form, so v is equal to angular velocity into r multiplied by r cross product with the position vector. Similarly, for acceleration, for linear acceleration, again remember that for velocity we were having only one component, that was along the tangent direction. But as we know that the velocity in the acceleration in case of curvilinear motion, it will have both components, that is tangential as well as the normal. Okay, so this is the tangential component, and this one is basically the normal component of acceleration, right? And we know that acceleration is given as time derivative of velocity, and we know that velocity can be given as omega cross r, right? So if you apply if you take derivative, so over here what we have, we basically have product rule, like derivative of first then into second, then first derivative of second. When you do so, what you will get, you will get this thing. By simplifying this equation, you will get a cross r minus omega square r. This a cross r is basically equivalent to the tangent component or tangential component of acceleration, and this omega square r is basically given by the normal component, and this is basically equal to the normal component of acceleration. Okay, so we can write the linear acceleration as a combination of tangential component of acceleration as well as the normal component of acceleration. And we know that the tangential component, that is basically equal to the angular acceleration multiplied by r, similar to like the previous one in which we were having v is equal to omega r. So over here the tangential acceleration is basically equal to angular acceleration into r, and this is further equal to dv by dt, right, as at is equal to dv by dt, and it is also equal to alpha dot r. Okay, and the normal component that is given by this equation, and we already know that that is equal to v square by r. So this was known to us, so this can also be derived from here. Instead of omega square, if you put its value as v is equal to omega r, so if we remove this one from here and put it over here, so omega will become v square by r, right? So if you put over here v square by r into r, so square and r will be cancelled out, and what you will get, v square by r over here in this equation. Okay, so if you look at these diagrams, for example, if you have a case like this in which we are having different gas meshing up, or in which we are having two pulleys, right, and they if they have a common belt, right, yeah, if we are having gas meshing like this, right, so in that case we can write this equation for linear velocity, linear displacement, and linear acceleration as theta s is equal to theta r. So we can write it for any two cases, means for this object 1, object 2, we can write as theta 1 r1 should be equal to theta 2 r2, and we can write as omega 1 r1 is equal to omega 2 r2, and similarly we can write alpha 1 r1 is equal to alpha 2 r2. Okay, so based on this, now we can have this example. Kindly give me a minute. Okay, now let's look at this example. What they are saying: a cord is wrapped around a wheel as shown in this figure. This is the figure. We have this cord wrapped around this wheel, which is initially at rest, right? So initially at rest when theta is equal to 0. So when angular position theta was 0, uh, the system was at rest. If force is applied to the cord, if we applied this force F to the cord and give it an acceleration of a is equal to 40, so means this acceleration is in terms of time 40, where t is in seconds, determined as a function of time the angular velocity of wheel, right? Means they are asking for angular velocity omega and the angular position of line OP, angular position of line OP, means they are asking for this one, they are asking for theta, right? So what we have over here in this equation, we have that magnitude of acceleration, and we know that magnitude of acceleration is basically equal to the tangential component, right? So over here that at is given, and we know that at is equal to alpha dot r, right? So instead of at we will put that 40, instead of alpha let alpha be like this, and instead of r we will put the radius 0.2. So what we will get, we will get this alpha value. So when we get this alpha value, what we can do, we can extract omega from here, right? As alpha is equal to d omega by dt, we know that angular acceleration is the equal to time derivative of angular velocity, and this angular acceleration is equal to 20t. So by doing the necessary integration, what we will get, what we will basically get, we will get the
Velocity,
we will get
angular velocity, angular.
we will get the angular velocity, right? Okay, so remember that initially the system was at rest, so that's why we put it 0, and then it had some angular velocity, that's why we put it as omega. Initially, definitely initially when it was 0, so this means the time was 0, and then at certain time the time can be given as t. Okay, so in second part, what they were asking for angular velocity. So we have identified, we have covered, we have find out the first part, which was basically the angular velocity, and in second part they are then asking for the angular position, that is theta. Now we need to find out this thing. Kindly give me a few seconds. Okay, let's come back to the problem again. Okay, here is the second part. I think it's displayed somewhere. Let's see it. Okay, it's given here. Now what we need to find out, we need to find out that theta is unknown. So initially when we were having alpha, so we used this equation, and from here we found out the omega. Now we are having omega, so we know that omega is equal to d theta by dt. So by taking this one over here, what we will get, omega d theta, dt is equal to d theta, right? So take integration on both sides. When you do so, what you will get, you will get this equation, right? The limits will be same again, and in this case, instead of omega, you need to put its value. So what was the value of omega from this equation? The value was 10t square. So you can put value of omega over here as 10t square. When you solve it, you will get the value of theta, that is 3.33 t cube radian, right? So in this case, all answer that we have, it is basically in the form of time, or it is as a function of time. And why it's function of time? Because the acceleration that we had, it was basically given as a function of time. But remember, in this case, we cannot use equation of constant angular acceleration, because alpha changes, the acceleration changes with time, means acceleration is basically function of time in this case. Okay, now let's look at this example. If the system starts from rest and the motor rotates with a constant angular acceleration of 2 radian per second square, so system was initially at rest, and this was basically the motor. This is the motor. It is rotating this wheel, and it is having an angular acceleration of 2 radian per second. Determine how much weight W has been lifted after the motor. Okay, how much weight? This weight is how much lifted. Means they are basically asking for the displacement of this weight. How much it is lifted? Has been lifted after the motor has turned 1 revolution. Okay, assume the belt and rope doesn't slip. Means this belt, mean there is no slippage between this wheel and this rope or this belt. It doesn't have any slippage, right? So we are having radius of this system, or this motor is given, the radius of this wheel is also given, and the radius for this section is also given, that is r wheel is equal to 0.3, wheel of rb is also given, and wheel that radius of ra is also given. So ra is equal to 0.15, rb is 0.5, and for wheel rw is basically 0.3. So what's they are asking, they are basically asking for s. Let's see if anything else. Meaning, if the system start from rest, the motor rotated with constant angular revolution, determine how much weight W has been lifted after the motor has turned one revolution. Okay, what has been given? One revolution. Mean it revolve, it start from here and it complete one revolution, right? So this means theta is equal to 2 pi radian. Okay, so now let's try to solve this problem initially. Okay, let's this system, as it is rotating, it is having rotation, so let the angular acceleration and angular velocity for this motor wheel or this motor pulley be omega a and alpha a, and for this system b or for pulley b, let it be omega b and alpha b, right? So in this case, we can use equation of constant motion, constant acceleration, equation of motion for constant acceleration. And that equation, as we know that for angular motion, we can write as omega is equal to omega naught plus alpha t, right? So in this case, omega naught was 0. So what we get? We will get omega is equal to alpha c into t, right? So omega a, that will become equal to alpha a into t, right? And we have this value of alpha a, and the value of alpha a is how much? That is 2 radian per second square. So when you put, so what you will get? You will get that omega a. Now let us consider any point on this rope or on this belt. Let's say we have this point P, some random point P. Now this point P is having linear motion, right? So the velocity of this point can be find out by using this equation: v is equal to r omega, or v is equal to omega r, right? So if we want to find out velocity of P, so this one will become Vp is equal to r omega, right? And this can be written as I have previously told you, that for such cases we can write this equation: omega r omega 1 r1 is equal to omega 2 r2. So the linear velocity, it can be given as omega a ra is equal to omega b rb, that is over here and over here, right? So means what actually I want to say, that the linear velocity of this particle over here will be same as the linear velocity of the same particle over here. Similarly, the linear velocity of particle P over here. So the linear velocity at this location, and at this location will be same. So that's why the linear velocity at this location and at this location can be made equal. So that's why I can write omega a r a is equal to omega b r b. And from here I can find out omega b, that is equal to r a by r b into omega a. When you do so, what you will get? You will get the value of omega b, and that is 0.6 t. So now we get omega a, and we also get omega b. Okay. Now let's say consider another point, but this is not on the same rope, not on this rope. Let's consider this point P. This point P is on the rope that is connected to the weight, right? So if I want to find out the linear velocity of this point, so again, I can use the equation V is equal to omega r omega. But in this case, this is for Vp2, right? So we will consider the angular velocity of this field, which is same as this one. So Vp2 is basically omega b into Rw. So when you put the value of omega b, you will get 0.18 t. If you want to find out the acceleration of this particle, so take time derivative of this thing. So when you take time derivative, what you will get? You will get 0.18, right? And as I have told you in initially, that how much revolution it have? One revolution means theta is equal to 2 pi radian. So when we are having one revolution, so this means theta is equal to 2 pi radian. That is basically equal to 6.28 radian, right? Okay. So now we are having this theta value, and we have basically AP2, right? And we are also having the velocity. So we can write equation of motion for constant acceleration, constant angular acceleration, that is theta is equal to theta naught plus omega naught plus half alpha t square. So this one is 0, this one is 0, right? We have only this term. So we already have alpha c, the acceleration from there, from the question, right? So when you do so, what you will get? You will basically get this value t is equal to 2.51 seconds. And then what we need to find out, we need to find out displacement, how much this weight has been lifted, this s. So far, displacement, we are having this equation, s is equal to s naught plus v naught. Why we are writing this linear equation? Because weight is lifted in the upward direction, so this means the motion is linear motion. So we can write this linear equation. So s is equal to s naught plus v naught t. This one will be 0, this one will be 0, and the only term that we have over here, that is AC. So AC is basically this acceleration, 0.18, and when you multiply it with t, you will get this thing, 0.565 meter. Kindly give me a few seconds, I have call from department. Okay, so now let's move towards another example. Here in this example, what we have, if the system start from rest, means the same system, and the motor rotates with the constant acceleration of 2 radian per second square, same problem. After the motor has turned one revolution, again same data, determine the magnitude of linear acceleration of point P on the wheel. Okay, this point P, linear acceleration. So it will be having two components. If if the rotation is like this, so one component will be like this, and one will be n. So we can have an and we can have at. So if we get this at and an, from here we will get this acceleration of particle p. Now the acceleration of particle p is basically required. So let's quickly look at it, that how we can solve. So from previous problem, that is omega was 0.60, right, and few other values, that t was 2.51. So we know these values from the previous problem. So t was 2.51 second and omega b was equal to 0.60, since we are having same problem. Okay, and we know that the acceleration, angular acceleration, it can be given as time derivative of angular velocity. So when you put that omega b is equal to 0.60 and take its time derivative, so you will get this 0.6 radian per second square, right? And we know that the tangential component is basically equal to alpha into r. In this case, we are having it for particle b. So when you have alpha b into r, we already have that r and we have that two value, so you will get this tangential component of acceleration. And we know that an is equal to omega b squared dot r. These are the value which we get from the previous equation. So when you put the values, what we will get, we will get that 0.68. Okay, when you combine at square plus an square, take its square root, so we will get that acceleration of particle. And this was the solution. Let me show you this equation. I have used these equations, right? I have used these equations. Now let's try to solve one of the problem from your book. Okay, when only two gears are in mesh, okay, gear A, this is gear A and gear B. Okay, when only two gears are in mesh, the driving gear A and the driven gear B will always turn in opposite, okay, in direction. In order to get them to turn in the same direction, what we need to do, an idler gear C is used. This is an idler gear, so that both gear A and B can have same direction. In the case shown, determine the angular velocity of gear B, when t is equal to 5 seconds, t is given. If gear A start from rest, so initially gear A start from rest and has an angular acceleration is given in terms of time, where t is in seconds. Okay, so what is basically required? They want to find out omega b, right? So this problem is like very much simple. What is given? Omega b is given at t is equal to 5 seconds, and acceleration of gear A is given, angular acceleration in terms of time, that is 3t plus 2 radian per second square. Okay, as we know that acceleration is equal to time derivative of velocity, same for angular. So what we can get by rearranging this equation, we can get d omega is equal to alpha dt. Okay, d omega is basically given by that equation, means over here we are having d omega, and instead of alpha, if we put 3t plus 2, so we get this equation, right? If you further solve it, means initially we were having no motion, the system was at rest, and then finally we were having some angular velocity. So definitely initially time was 0, and then final we can put any time t. Okay, so again this final time t can be put as equal to 5 seconds. So when you solve it, what you will get, omega a is equal to 1.5 t square plus 2t, and as I have told you, t is equal to 5 seconds. So at t is equal to 5 seconds, we get omega a as 47.5 radian per second. But remember, we want omega b, not omega a, right? but we get omega A. So from this we can find out omega B. So how we can move from here till here? We can move through this step, right? Okay. So as we know that omega A, first let's use this step. Omega A R A is equal to omega C R C, and then we will use this one. Omega B R B is equal to omega C R C. Okay. So by doing so, we will find out omega C. Once you find out omega C, then we can use this equation omega B R B is equal to omega C R C, and from here we can find out omega B, right? So this is basically required, that omega B was required, and it is 31.7 radian per second. Now here we have these two questions, so the answers are given. You need to solve this problem, and once you get the answer, then you need to match it with these options. So the closest match will be your final answer. Again, same for this one. You will select an option that closely resemble your answer that you obtain after your necessary calculation. Okay. Um, Again, since I have told you we are doing chapter 16 of RC Hibbeler, so you need to go through example 16.2 and the problems F16.6, similarly 16.5, not F16.5. And apart from this, you need to look and you need to go through all related problems and examples. Okay, so this is the ends of lecture from my side. If you are having any question, you can ask.
एक्सक्यूज मी सर।
जी जी।
सर यहाँ पे हमारे पास वी और लीनियर वेलोसिटी और लीनियर एक्सेलरेशन के दो फार्मूले, एक क्रॉस में और एक डॉट में। तो डॉट वाले हम सिर्फ 2D में इस्तेमाल करेंगे।
नहीं, डॉट हम उस वक्त, if you are interested only in magnitude, right? And if you are interested in vector form, if the output required is in vector form, so आप फिर क्या करेंगे, आप क्रॉस प्रोडक्ट लेंगे। अगर आपको याद हो, मोमेंट के केस में भी हमने ऐसा ही किया था, बल्कि if you recall
जी
your
सर।
previous lecture, उसके स्टार्ट में
यस।
भी ये चीज हमने एक्सप्लेन की थी।
यस सर।
याद आ
और
गया
सर
कुछ?
ये आर, यस सर, और ये आर क्रॉस ओमेगा नहीं होगा? वी इज इक्वल टू आर क्रॉस ओमेगा।
uh, it is basically omega cross r, not r cross omega.
ओके सर।
Okay, anyone else?
नो सर, इतना ही था। थैंक यू।
ठीक है, चले रिकॉर्डिंग में ऑफ कर देता हूँ।